Hey guys, let's do another conservation of mechanical energy problem. A block of mass m slides without friction along the loop track as shown below. If the block is to remain on the track, even at the top of the circle whose radius is r, from what minimum height h must it be released? Okay, so there's a couple of key words in this question I want you to be paying attention to. Okay, the first is, at what height must it be released? When you hear something like that, you should immediately be thinking that its initial speed is 0, that initial speed that it's let go at. And the second is what minimum height. So let's inspect what's happening in this loop. I mean, you've got the block, it's being released from rest, goes down through the loop and back out again. And we want to know the minimum height to release it so that it's still able to go around the loop. I mean, think about it logically. The higher and higher up you release this block, of course, it's going to go through the loop. You can just keep making it higher and higher, h larger and larger. But what is that smallest h that it'll still go through the loop? And so this is what's happening when you take a look at the physics of the block when it's upside down in the loop. Okay, so here you've got the block, and when it's upside down, you've got the normal force going down, and of course you have its weight going down. And since both of these forces point towards the center of the circle, they both represent the centripetal force. So in this case, the centripetal force is Fg plus Fn. And the idea is, in order to have the minimum speed or the minimum height, you need to have normal force going to 0. Because at that point, it's just barely going to graze the top and come through. So Fn becomes 0. So in other words, your centripetal force equals your force of gravity. So let's simplify this a bit more. mv squared over r is Fc, Fg is mg. Okay, so you get a nice cancellation happening there with the masses, which is good because we haven't been given the mass on the problem. Okay, so now we have an expression for the speed that we can solve for. So v is equal to gr square root, right? This is an expression for the speed at the top of the loop, so right here. So why don't we call that instance v2? So v2 is equal to square root of gr. Now, we don't know what r is because we've just been given that in the question as the radius is r. In other words, you can apply this situation to any problem with any radius. Okay? And I see a conservation of energy problem happening here. I've got a speed here, and because the radius of this loop is r, right? So technically then the height at which this thing is at here is 2r because you've got two r's right there. So h2 is equal to 2r, right? And we're trying to figure out what h1 is, given that v1 is 0. So you've got 4 different things here. Hopefully you see that conservation of energy solution coming about. Okay, so we're going to use this as point 1 up here and point 2 right there above the loop. Okay, so these 2 points right here. So let's do our conservation of energy expression. ET1 equals ET2. And the 2 types of energy we're dealing with here are gravitational potential and kinetic. Okay, so ET1 is EG1 plus EK1, ET2 is EG2 plus EK2. If you want to go ahead and just start writing in exactly what you know the energies are, go ahead. I prefer to write everything out and then cancel it out as I go along. Okay, so EG is mgh1 plus 1/2 mv1 squared equals mgh2 plus 1/2 mv2 squared. Okay, so now we've got our long expression. Let's do some canceling. Okay, first things first, there's a m term in every single part here. So I'm going to cancel out the mass. Again, imagine factoring out the mass from left and right and then canceling it on both sides. And it's good because we weren't given the mass in the question, so it's irrelevant piece of knowledge. Okay, so v1 is 0. So if that's 0, 0 squared times anything is 0. So this whole thing disappears. So that's convenient. So we're left with gh1 equals gh2 plus 1/2 v2 squared. Okay, now v2, remember, is root gr. Okay, so v2 is root gr, so therefore v2 squared is just gr. Okay, so let's substitute that in. gh1 equals gh2 plus 1/2 gr. So now hopefully you see that now g appears on every single term. I'm going to cancel that out. Okay, so all you're left with is h1 equals h2 plus 1/2 of r. Really simple expression we've come down to. Okay, so h2 we said was 2r. Okay, so 2r plus 1/2 r is 2.5 r. Okay, 2.5r is the height, so regardless if the radius is 1 meter, then it's going to be 2.5 meters as the height. Okay, so that's it for this problem, guys. I hope you enjoyed it. Be sure to smash that like button if you liked it, and be sure to stay tuned for video 110, Conservation of Mechanical Energy 4, to be posted tomorrow at 12 noon. Hey guys, that's it for this episode. If you enjoyed it, be sure to check out some of my most recent videos posted over there on the right, which you can click on your screen right now and watch. Other than that, guys, I hope you enjoy the rest of your day, and I will catch you in the next video.